I'm sorry, guys. I know I've been late, and really, I tried my best to make it here. A lot of traffic. Obviously, I don't want to make my years late, right? My live class is late, but I'm really sorry. So my apologies. We're going to be studying this today. This is what you call a standing wave. You see that? That's a standing wave, right? And this is exactly what we're going to be studying about. This is basically a standing wave. I hope you guys can see that. It's pretty clear, very easy to understand. So before we go into explaining this, what I would like to do is show you this. Basically, it's a visualization, and it's very helpful because it makes life much easier. So what I want you to notice here is there's basically two progressive waves moving in opposite directions. There's a blue one going from left to right, and there's a red one going from right to left. So there are two waves going in opposite directions, and what happens is they interfere with each other at different places. So if we look at this, and if we try to go backwards with this, as in let's try drawing this. The thing is that obviously you can't draw something that moves, sadly. So, and even if you did, you'd be like Harry Potter. So we're going to be using these three colors to represent the three waves, all right? One possible position that this wave has is that the blue wave can be like this, right? And the red wave can be like this. So what's the phase difference between them, Ki? That's about red tech to baja, I guess. I know. So what's the phase difference between the two?
180.
180. So what are you going to get? You're going to get destructive interference, right? Because we've studied that previously, that a 180-degree phase difference creates a destructive interference. So basically, what are you going to see? If this is the wave, if the resultant is the black line, then the black line is going to be flat, right? And this is exactly what we see happening here. Do you see that? When the blue wave and the red waves are 180 degrees to each other, it creates a moment there. It's a moment where it's exactly 180 degrees phase difference, right? So that's basically what we get here. Right, that's one scenario. In the next scenario, as you can see, the blue one's moving along this way and the red one's moving this way. We can draw that too. So say in the next scenario, we shouldn't be using blue for the wave structure. Should we could use gray. Yes, let's use gray. So again, blue one's moving to the right. So what we're going to do is next moment, a little bit more of the wave goes along. We get this. And the red one is moving to the left, right? So if we say the red one moves to the left, then this trough would move on. As you can see, it's moving. So what we get is this. What's going to be the resultant of these two, Kashmir?
Constructive interference.
Yes, very good, because they're in phase. And what's going to be the wave you're going to see? Basically, you're going to see this, right? Have you noticed that I've drawn much larger than any one wave?
Okay.
Why?
The vector summation.
Yes, it's the vector summation. Damn, man, you know the words really well. So basically, it's the vector sum of this plus basically this much. I'm just translating it to here. Then again, you have this. My wave's a little too bigger than expected, and basically these two. So this is the addition of these two gives us that, and the same thing happens here. So this is again, if we go back to this, you will notice that at any point when the waves are in phase, the black resultant wave doesn't really match at that point. It's even higher than that. So why is it higher than that? That's because it's the sum of the red and the blue waves. So that's basically constructive interference, right? So that's situation number 2. So we can draw that here, right? Really simply by just drawing this, right? Next situation is if it moves a little more, again, you get basically this interfering with this. I'm just going a little faster now because I think pretty much everyone got it, right? Destructive interference, flat line. And then last scenario would be where we have this interfering with this, right? And that's going to give a resultant wave, which is basically this. Oops. Like,
yeah, there.
Kagod shesh, like, So basically, that would basically become this. So now, obviously, we can't draw all of this. Like, if they say standing wave, we can't start drawing all of these in different colors and everything. So we draw this really simply, actually. We draw this in its very simplified form, which is basically a representation of this. And that would eventually become there you go. That's a standing wave. Right? Do you get that? So these points never move. They're called nodes. Right? This is a node. This is a node. This is a node. And even in here, if we look at our GIF, it's called a GIF, you can see the nodes. They're basically those red dots. So the red dots are basically the nodes. And when we draw it like this. And the distance between the two nodes, basically this region, is what we call antinodes, right? These are the points where you have maximum displacement. Really easy. So if you want to know lambda, for example, you'll notice that the distance between two nodes represents only half of the progressive wave which is making it. So one whole lambda is actually this, right? Do you agree with that? Like, let me show you from one node to this node. This is going to be one whole wavelength. So if that's the case, that basically means internodal distance is half lambda. Two nodes is lambda, right? So that basically means if I draw, say there's a string and I create a standing wave on it. That's a horrible wave, totally ugly. So yes, don't make fun of it. So that means this much is half lambda. And the whole thing is lambda, right? Really easy. Now, what would happen if I was to take the string and if I tried making a wave which was even longer? Say, for example, I take a string and I create a wave like this. What would this be? If the string's length is L, the string's moving like this. No, not 1 by 4, half L. Lambda is equal to half. Sorry, whoops. Lambda is equal to 2L. Right? Because this is half lambda, so the whole thing would be 2 lambda, right? 2L, sorry. So say this happens at frequency F. Now what I can do is, I can increase the frequency. And as I increase it, our heebie-jeebie is going to be a mess on the string. But ekta point a same string, I'll get a wave like this, right? Where this is basically L. So lambda is now equal to L. And what's going to be the frequency which causes this? It's going to be 2F. Does this make sense? Obviously, this has to move faster. Moshe. Hey, Moshe. Just went through our class. And if you take this further, it'll be something like this, right? Tokhon khayal karo. This is lambda. If the string is L, then lambda now is how much? Come on. It's going to be 2 by 3L. And this is frequency 3F. Does that make sense? Right. So we can take this even further. If we were to draw, say, like, 4F, what's going to happen at 4F? You'll see this. Or even 5F. So this is going to happen at 4F, this is going to happen at 5F, and it keeps going. So let me show you a couple of these animations so that you understand how these standing waves work. All right, so basically, you can see this, right? And if you notice this, this is basically the first scenario, which is this, light at the com. So in this scenario, we basically have this going on. The second one is this, third one is this, fourth one is this. And an interesting thing you'll realize here is that this is moving at a frequency which is 1/4 the frequency of this. Basically, this is moving 4 times faster than this. And that's why, this is moving really slowly. And the others are actually moving This is twice as fast, 3 times as fast, 4 times as fast. So that's basically what's going on. Is this clear? All right. All right. Any doubts there, guys? Any questions, any queries so far, Dr. Kaslam? So, here's a couple of interesting things. Number one, if we take this point, hey, guys, leave. If we take this point on the screen, what happens is the amplitude is here and here for the antinode, right? But you notice one thing, that only the points on the antinode, only the points on the antinode move this distance, right?
Not all of them.
Oh, the other points don't even move this distance. Okay, this is getting annoying now. So what you see is only the antinodes move with maximum displacement. If this was a progressive wave, if this is a progressive wave, for example, every point on it eventually does reach maximum displacement. If this was a string, all the points of the string does reach maximum displacement. So that's number one in differences, that only antinodes reach maximum displacement for a standing wave, and all the points on a progressive wave reach maximum displacement. So that's number one. Number two is nodes have zero displacement, right? There's no points like this on a progressive wave which has zero displacement, right? Another important difference is, if you see the points between two nodes, they're all in phase kintu. They reach maximum together, they reach minimum together. Maximum together, minimum together, right? So maximum or minimum je eksathe hocche, you're going to notice something, that it doesn't have to be ye kintu. Mane in phase doesn't necessarily mean they have to have all the same amplitude, but it means that they're at the same point in their cycle. So basically lowest point, highest point, lowest point. So this is another very important difference. Points between two nodes are always in phase, and points across the same node are always anti-phase. Does that make sense? So yeah, that's pretty much it. These are the differences for amplitude and I think lambda equations to 2 by 3 Kano. Lambda equals 2 by 3 Kano. Oh, this one. That's because, really easy, we know that node to node is half lambda. So the whole string, if it's L, is 1.5 lambda. Because this is half, this is half, this is half, if you add them all. So basically L is equal to 3 by 2 lambda. So lambda is equal to 2 by 3 L. And it's also visually pretty obvious in the sense that this is 2/3 of the entire wave. Right? That's that.